All right, let's jump right into it. Have you ever wondered what exactly is happening on a microscopic level when you grab a hot cup of coffee? Or why a simple desk fan actually cools you down on a sweltering day? In this explainer, we're diving straight into the hidden mechanics of heat transfer. It's a foundational field of engineering that literally shapes the physical world around us. So, picture this. You drop a red-hot steel bar into a standard pail of water. You already know intuitively how this plays out, right? The steel cools down, the water heats up. Simple. But answering exactly how long that process takes, well, that requires a fundamental shift in how we look at energy. We aren't just asking what the final temperature will be, we're asking about the journey. How rapidly does that energy actually move, and what rules govern that speed? To really understand that journey, we kind of have to contrast two closely related fields. Thermodynamics tells us the final amount of energy at equilibrium. Think of it like knowing your starting location and your final destination. But heat transfer? That's the actual science of the trip itself. It deals with systems that are specifically not in equilibrium, giving us the mathematical rules to predict the exact rate at which that energy exchange happens over time. To make sense of the math behind all this, we're going to break heat transfer down into three distinct, super intuitive physical mechanisms: conduction, convection, and radiation. And then we'll wrap up by looking at how engineers actually measure all of this in the real world. Okay, first up, let's look at conduction. This mode is all about direct physical contact. In simplest terms, you can think of conduction as a microscopic domino effect. See, we identify the kinetic energy of a molecule with its temperature. So in a high-temperature region, those molecules are moving fast. When they're packed tightly together, the fast, hot ones smash into the slower, cold ones. And during these constant, random collisions, they enthusiastically pass their kinetic energy right along. It's the literal physical transfer of energy through a material, without the material itself visibly moving at all. Now, when we map this out, notice how that temperature profile line slopes downward. That negative gradient is absolutely crucial. The math literally requires a minus sign there to satisfy the second principle of thermodynamics. It's basically just the universe's way of ensuring heat always flows downhill on the temperature scale, from high to low. And the steeper that slope, the faster the heat conducts. But the actual physical material matters immensely here. In gases, energy moves via those random molecular collisions. In liquids, tightly packed molecules and strong force fields take over. Solids, though? Solids are fascinating. Good conductors like copper use a sea of free electrons, what we call an electron gas, to rapidly transport heat. That's exactly why good electrical conductors are almost always incredibly good heat conductors, too. Now, check out what's really interesting here, the diamond surprise. Look closely at these numbers. Silver and copper are fantastic conductors, sitting around 400 watts per meter per Celsius degree. But look at diamond. It sits at a staggering 2,300. Even though diamond is an electrical insulator, its incredibly tight crystal lattice allows it to conduct heat up to 5 times faster than pure silver. Actually, this is the exact trick jewelers use. They touch a thermal probe to a stone, and if the heat pulses away instantly, it's a true diamond. If not, you've got a fake on your hands. Let's see how this all builds when we compare gases to liquids as they heat up. When we chart typical gases, we see that a gas's thermal conductivity generally increases pretty smoothly with the square root of its absolute temperature. Why? Well, hotter means faster, and faster molecules transport energy quicker. Simple enough. But for the liquid phase, it's way messier. Because liquid molecules are so densely packed, complex force fields make their thermal conductivity far less predictable as those temperatures shift. All right, let's shift gears to convection. This is where the medium itself actually starts moving. You probably intuitively know how convection works. If you've got a hot plate of metal sitting in a still room, it cools down slowly through natural convection as the heated air rises off it. But put that same hot plate in front of a blowing fan, what we call forced convection, and it cools down way faster. The fluid motion of the air is actively carrying heat away from the surface. But look really closely at this flow profile, because this is where it gets kind of mind-blowing. Right at the microscopic surface of the hot plate, the fluid velocity actually drops to absolute zero. It completely stops. This happens because of viscous action, basically friction between the fluid and the solid surface. So because the fluid layer directly touching the wall is perfectly stationary, the heat must conduct through this tiny layer first, meaning this entire moving process relies on a microscopic, foundational layer of pure conduction. Crazy, right? So the crucial takeaway is that a faster fluid velocity essentially shaves down that stationary layer. It creates a sharper, steeper temperature gradient right at the wall, which lets the moving fluid carry the heat away so much quicker. We calculate this overall cooling effect using Newton's law of cooling. It relies heavily on a variable called the convection heat transfer coefficient, just represented by the letter H. That single little variable encapsulates all the incredibly messy physics of viscosity, fluid density, and flow speed. Moving right along to radiation, this mode strips away the physical medium entirely. Unlike conduction, which absolutely needs physical contact, or convection, which requires a flowing fluid, thermal radiation doesn't need any matter at all. It travels purely via electromagnetic waves. This is the profound mechanism that actually allows the sun to warm the Earth. Thermal radiation can completely cross the absolute void of a perfect vacuum to deliver heat. The math here is governed by the Stefan-Boltzmann law, and it hinges entirely on this very specific number, 4. The law dictates that an ideal thermal radiator, what physicists call a blackbody, emits energy proportional to its absolute temperature raised to the 4th power. That means if you simply double the absolute temperature of an object, it doesn't just radiate twice as much heat. It radiates 2 times 2 times 2 times 2, 16 times as much heat. The scaling is just massive. But there's a catch. True, ideal blackbodies, they're basically theoretical. Because real-world objects aren't perfect blackbodies, we have to adjust our equations. Our sources note that a glossy painted surface or a highly polished metal plate won't radiate nearly as much energy as a true blackbody at that exact same temperature. So, to calculate actual heat transfer, engineers introduce a modifying factor called emissivity to account for the gray, glossy, or polished natures of the materials we actually build things with. Finally, let's talk about measuring heat in reality. How do we actually tie all these complex molecular collisions and invisible electromagnetic waves back to the physical world? Well, engineers rely on exact, standardized SI units to make these invisible forces predictable. By measuring heat flow in watts, which, by the way, are just joules of energy moving per second, and measuring thermal conductivity in watts per meter per degree Celsius, they can safely design our modern world. These fundamental units are the exact same tools used to design everything, from the insulated thermos that keeps your morning coffee hot, right up to these super insulated cryogenic fuel tanks on spacecraft, operating at negative 250 degrees Celsius. It's the exact same math. So now that you have this framework, I've got a challenge for you. Look around your room right now. Feel the temperature of your desk, notice the air blowing from your vents, or feel the warmth of the sunlight coming through your window. Can you figure out the physics at play? Are you feeling the domino effect of conduction, the moving fluids of convection, or the invisible electromagnetic waves of radiation? The science of heat transfer is happening all around you, literally every single second. Thanks for joining me on this explainer, and keep questioning those invisible forces in your world.